Good evening, everyone. Welcome to this third and last satellite event of Order of Operations. As you know, Order of Operations is an exhibition that is currently at Bozar Lab, which we co-produce with Bozar Lab. We are Ohme, an art science production company. The last day of the exhibition is tomorrow, so if you have not seen it, this is your last opportunity tomorrow. So in this last satellite event, we have the pleasure to organize an event on the theme of creative mathematics, ending with an algorithm. We had the chance to have a superb workshop this afternoon about creative coding with Saskia Freke and Timo Hoogland. And now we have the big pleasure to host a talk van Frederik Vanhoutte, who is a physicist during the day at the University of Ghent and a creative coder at night, maybe more than night. And we have also the immense pleasure to have his design as the poster and animation related to the exhibition. So please give him a round of applause to Frederik Vanhoutte.
Thank you, Nicola. Yeah, I just mentioned it before we started that I had the opportunity and the good fortune of being able to contribute to this exhibition, not only with a series of plots which are called Add Nothing, Subtract Nothing, which are in the exhibition, but also I was asked if I could provide some material for the scenography. And so yeah, these you have been staring at and you're fed up with them, so let's kill those. And in addition to those, there were quite some compositions made. And these two I actually call together Honderdveld, and as promised, I'll talk a bit about them. So let's start this presentation. I am not a live coder, but it is code running live, but it's written before. So when they asked, would you be able to do something for the satellite symposia? I mean, the subject material is quite obvious. It's creative coding. I'm here on stage as a creative coder, which is indeed something I don't do professionally. So I'm not a professional coder or artist. I am not a mathematician. I'm not an art historian. So I'm in a unique position that I can be wrong in 3 fields at the same time. So that's good. But to talk about generative art and some mathematical principles without making it a math lecture, because as I said, for me mathematics is a tool. It's something I see the beauty in, but I don't have real in-depth knowledge about it. You can find me on social media under the moniker of WBlut. So that's one thing that's a bit of a redeeming feature, I guess, is that I've been doing this for a very long time, about 17 years ago. So please be careful in what names you choose when you start something, because you're stuck with them for a very long time. But this is so mostly active on Twitter nowadays, and Instagram serves as a kind of image archive without too much comments, just adding on it. Behind the curtains, I'm mainly using processing. This, if you're familiar with it, I think so. It's something that it's now in September going to be 20 years old. I've not been working with it 20 years. I've been working with it for 17 years. And in fact, what it looks like, if you have it on your computer, mine is a Windows computer, but it's available on other machines also. It's a kind of interface that allows you to write some scripts, to write code. What's running behind is Java. That's what is running everything behind the screens, but it's hiding some of the more annoying complexities that you need to get started to draw a line on a screen. I mean, that's not something fundamentally in programming languages and lower level programming languages. So it takes away that bother. And for me, it's actually what I use it for. So for me, it's a way to write code and not really worry about how this white pixel appears on the screen in the right place, and not having to wonder how I have to drive this video card. And the nice thing, of course, with processing and processing JavaScript and many other environments that are out there is that you can just share the code with other people on other platforms and don't have to worry about what they are running it on. In fact, the work I make, all the digital work, is done in processing. in this kind of scripts. And the presentation I am running, that's the same code that it's running. It's been modified to run as a kind of a slideshow presentation, but it's still everything that will be moving, everything that is interactive is the processing code which has been transplanted into this presentation thing. So yes, my presentation can freeze, it can crash, and its frame rate can drop. Okay, so generative art. It's a bit a difficult term to define because it's art. And this is an attempt that I saw pass by, I think, let's see, yeah, last week, something like that, by a professor of computational arts, they exist, and artificial intelligence, Simon Colton, where he tries to find some kind of order, some series of boxes to put in art, and immediately I didn't really like it. Because yeah, you have visual art, computer art, generative art, artificial intelligence art. So, of course, the context is important. The context of this graph is trying to put certain techniques of artificial intelligence and machine learning art into broader perspective. So this graph is made as if it's top down, but it should be read from the leaves of AI to the roots higher. Because of course there is computer art that is not visual art. There is generative art that is not computer art. There is computer art that doesn't fit in it because he defines computer art as something with computational means. And I don't really agree because computer art is art using a computer. And it's a strange term because we do use it. We talk about painters and sculptors. Painting is brush art and sculptures is hammer and chisel art, if we use the same terms. But even if we look at painting, we have a broad range of how we name things. We have things which are really going to techniques, like pointillism is a certain technique. There was a brief philosophy around it, but it's mainly technique. On the other hand, you have expressionism, impressionism, which start with a philosophy, and where the technique is second, I would say. And you have something in between like cubism, which combines both. So what is it for generative art? Is it a medium? Is it a technique? Is it a philosophy? I would definitely say that generative art is not a medium. It's not computer art. It's art using algorithms, using procedures, but there is a lot of art out there using computers which is not generative. We have, and it's exploding for the moment, we have digital painters, we have digital sculptors, we have people creating entire worlds digitally on computers, and that is most definitely computer art. Is it computational art? Are they using anything beyond the ability of the computer to display and make these images, or be a replacement of canvas and paint? Maybe not, although it's a gray area. On the other hand, you have what I would call generative art. And for me, generative art is art where we do not start from a vision, an image we want to create. We do not want to make Theseus escaping the labyrinth and there try to find that, try to make that. And make no mistake, even in non-generative art, the medium and the tools and the techniques will definitely influence the result, and it will influence the path that the artist takes. It's not independent. Generative art distinguishes itself, I think, as a technique from the fact that you start from a basic principle, a rule set, something that you want to explore, that you want to follow, not from an end result. For example, these particles running around. Is generative art computer art? Mostly, yes. But it doesn't have to be. Generative art can exist with pen and paper. It can exist within a crowd. It can exist with a number of stamps, an audience, and a wall. Preferably with the venue knowing about it. So it's all possible. Of course, we have a kind of bias to generative art. We see it's mostly computer-based, but then again, what we are looking at is mostly computers. And there were, in the 18th century, we know that there were composers who had generative music, who wrote pieces which you had to roll a dice to know what the next section would be. For all we know, in the 16th century, in the woods of Finland, somebody was making generative art with the rocks and trees. We just don't preserve it, and that's something that we always have to take into account when we discuss art. The art history, the things we consider as basis of our culture, are what has been preserved. And what has been preserved for us is mostly art commissioned by rich people and institutions. So we have a huge bias in what we consider to be art. And I'm quite convinced of that, many of the things we have invented in the 20th century as these kind of dynamic arts, these participation arts, performance arts, these abstract forms of arts, these have been reinvented again and again and again, because they are not preserved. So, if people are curious, I have my notebook with me, with my generative dice experiments. It's something I did by necessity when my previous computer blew a fuse and started giving black smoke, which was not what I wanted. So I didn't have a machine, and I had 20 minutes a day to fill. And normally I fill this with the computer, with coding and processing. So I work with dice and a notebook and pencil. And in the beginning, I took physical dice on the train. That's a bit of an experience. It's fun to do. I mostly done that now during COVID, so you have the train for yourself. Yeah, you have to come on stage if you're too late. That's my son. So. Nowadays, I have to say that I cheat a bit, and I have a dice app on my phone, so I can be a bit more discreet, but still. It's really a fun exercise to do. Right. Generative, starting from simple principles. So I'm going to focus, I'm going to build up. I have no idea how long I'm talking, by the way, but I'm going to build up to the pieces I made for this exhibition for order of operation. And it starts with a simple triangle. And it's always a good way to start explaining is make it as simple as possible. And I think this is, it's the simplest polygon that exists. And the rule I want to apply is I want to subdivide it. And I have a rule to subdivide it. And this is not really exciting. Now I have 3 triangles, and the system knows how to subdivide triangles, so I can do it on and on and on. Okay, this is a nice rule. One problem with this rule is it always gives the same result. You can also do it by hand. There's no reason not to do it. But if you do it 10 times, you have 10 times the same result. It's not much fun. Where generative art starts to excel is when you start building in branches and choices. And there's many ways of subdividing a triangle. Some of them are here. Some of them, the ones I chose, are here, or a square, or a pentagon, a hexagon, octagon. And these are all kinds of ways to subdivide these. So I always end up with 3, 4, 5, 6, or 8 corners. So I can always repeat the rules. And then the nice thing is we can just have the system run, doing 1 iteration, 2 iterations, just have it randomize. Or use other shapes. So as a technique, there is a strength there in the fact that you set up certain paths, but you let the system follow those paths. I don't have to manually in my notebooks trace all these possibilities. Sometimes you have to do, because there's a lot of knowledge in doing things manually. And you can take it beyond. And basically, you have a recipe that creates these kinds of things. And it's often said to be the strength of generative art, that every execution, every part, every time, it's unique. Now, in itself, that's true. Every one of these is unique, and we will never see the same one twice. Those chances are astronomically low. There's just too many perturbations, too many possibilities going on for this to ever repeat. Now, I wonder if that is really an inherent value of something, because if I prepare a bowl of oatmeal in the morning, every morning that's a different bowl of oatmeal. If I would take a picture of it every day that would be not the same bowl of oatmeal, but they would all look the same. So we have to be careful. Uniqueness does not equal interest. So it's always about striking a balance. The second thing, and that's a personal opinion, that's something I have found, is that the most interesting pieces always have different scales in it. I find that using one scale of feature, whether it's in a building, whether it's in a story, whether it's in an image, whether it's in music, is not very interesting. And it's if people ask me advice about generative art and about their work, it's something I always say, always work on different scales. Don't have a single feature at a single length or time or whatever. Okay. And this can be used to make your GPU smoke a bit. This is still processing, and I quite like it. And nowadays, it's definitely possible to do this in manually, block by block, render it out in programs and time these animations manually. But I think it's very useful to have this kind of methodology as an exploration. And it's something you often see, that generative algorithms, generative approaches are used to find a design, to find a feeling, and that then this is manually reproduced. Yeah, here you see what's the danger of being random is that sometimes you get huge features and sometimes it's very, very tiny. But in this case, we are a bit lucky. It's one of the reasons I always accept invitations to speak. It's just to see these pieces on a big screen. I don't have this kind of screen at home, so. And this is an actually excellent venue to have this. Okay. Not sure if the black pause is I myself that put in a pause or that I just crashed my presentation. That's always interesting. Right, I actually don't know. The starting point for the work of order of operations was not a triangle, but it was something almost as basic, namely a square grid, a 10 by 10 square grid. And it has connotations with mathematics which are not really universal, but for example, in Flanders, I don't know for sure in French-speaking Belgium if the same, but one of the things which is being used to teach 7-year-olds insights in the numbers and how numbers relate to each other and what they represent is the 100 field, het 100-veld. And I thought that was a nice starting point to do it. Now, if we would take this as a classical approach, something non-generative, then you would have these 11 by 11 points, which are kind of fixed. And you have to connect them up, and that's your grid. Now, there is one 10 by 10 grid like this, so this design is done, finished, there is no variations. So how can we build in variations? And one of the first tries you could do, one of the first approaches, which you also could do in paper, is like, what if I slightly shift some of these points? It changes this appearance and more or less, and every time you do it, it's different. It does have a high bowl of porridge appearance though. I mean, pure noise is not that interesting. The other thing is that we don't have control. Pure noise tends to make a mess, which loses the coherence. And it might be something you're looking for. This might be the look you want. And sometimes mess is what is needed. But in this case, it's what wasn't what we were looking for. So this direct approach of manipulating this 100-veld was not working. So are there other approaches? Are there approaches beyond this very static one? Well, to do that, we have to do some work in the computer. First of all, before we can go beyond our paper notebook, we have to have a system. We have to tell the computer what is a point. Luckily, we have frameworks to do it for us. Once we have that, once we can define things, we can draw whatever we want. So this is also what enables digital painting, digital sculpting, digital scenery in computers, of course. But why stick with 1 point? Why not go to 2 points? That's the next step. Because 2 points can be connected to each other, and 2 points define a line, a direction. And once where you have direction, you have motion. So the fact, so we start with position, with points. Now we have direction, movement, animation, force. All these things are enabled by just having a second point. We can then have points running around. In this case, we have forces, and the points want to be in the center, and there are some invisible obstacles, and there were some coding errors which resulted in these very nice lines that we got, so we kept them. And you can start exploring these kind of animations. Nothing in this system, when it was started, was made to create this image. If somebody would take a screenshot of the image and you give it to a group of people working on a computer and you ask them, make this image, you will have a huge amount of different approaches. And actually it would be an interesting experiment. And this one is probably still somewhat doable. If you go a bit more whimsical and you go to define your own, let me find a good viewpoint. It doesn't work while looking back. This kind of particle system, it's the same as what the other one was doing, just in 3D, and the rules have been a bit different. If somebody had to find out the rules which are behind that, that is not possible. I hardly know how I did it. The reason for that is that some of these very specific behaviors, like some of these particles are switching trails. It's like they're moving on one line and suddenly they're skipping to another line. There are no lines defined. These are actually coding errors that for some reason give you that appearance. This is a non-physical realistic simulation because the physicist who wrote it made a mistake. But it's great fun. So that's what motion, force, direction gives us. So if 2 points give us that, what do 3 points give us? And 3 points give us triangles. And the triangle is quite special, because there's one thing you know about 3 points, and that's 3 points, if you choose them not malignantly on the same line, if you choose them quite generally, you define a plane. And the triangle is the only polygon, the only shape where you are guaranteed that it's flat. If you have 4 points, there is no guarantee that these 4 points are on the same plane. And computers don't like that. That's why triangles are very essential, and are also the elements that gives you the ability to model anything in a computer. Whatever method you use, however complex it is, in the end, when the computer has to show it on the screen, you will see triangles. At least that was true until a few years ago, when other techniques became available, but still it's dominantly triangles. And by building that, we have points, we have direction, we have planes. We are building up a library of concepts which are all mathematical, because there is no way to have a computer interact with lines and planes without describing them mathematically. I have a line here, I have a plane. I can draw them, but where the two intersect, the code doesn't know. Even if the code gives you functionality to draw a line, it will not give you the functionality to show what the intersection is of a line with an object, because those lines, the objects, have to be described in a way that this can be found. And that's the mathematics behind it. And it's not that scary, actually, the mathematics behind it. I don't know if people in the audience are from a more mathematical side, and if the other people are more from an artist side, and then you have We are all a bit on that spectrum. There is often this threshold from mathematicals that kind of freezes us, but there is an incremental step-by-step approach into it. And I think for me that was doing this kind of creative coding in the generative art. And if we are able to do that, it unlocks more and more possibilities, and it builds upon each other. So suddenly you have the possibility to find out where things hit each other and intersect, and not because you want to avoid it, but just because you want to draw it and make these kind of images. But what it also does, it gives you a new approach. Instead of seeing the grid as something which has been fixed, determined by those points, you can see it as something larger that has been divided, something that has been sliced up. Because if you see it that way, you suddenly have handles to manipulate, to have more control over it, without the system becoming a mess, without becoming chaotic. So instead of having these very local changes, now we have changes across the entire grid. So this was another option to have these kind of lines. And the nice thing is, it does remain, there is order. There is still order in the system. What I didn't like is that it distorted the proportions, and so we went beyond that. Now, if you work very specifically on a project, if you do creative coding, it's very hard to stay on track. So you find out that you have myriad ways of procrastinate, and instead of going to the goal you want, you start playing around with the system, like instead of having it slice everything, let's just slice half of them, and you get this kind of semi-patterns, which I like very much. The reason I like these more than the others is that also here you have far more evident this difference in scale of features. And you can use it to create things like this. So all the decisions that have been made here, because sometimes people say generative art, computer art is art by a computer, not by a person, but all the choices, how this appeared, are of course made by an artist, by someone, or in this case by me. And what the computer does add is, having built the system and the way the colors are assigned and how the animation goes, it doesn't take a lot of changes to completely change the appearances. The only thing that changes here are the lines on which this black screen has been divided. That's it. Or the artificial symmetry that has been imposed. So it's a very, very powerful technique to explore. If you build a system and you make sure that you can adapt the system, you will keep carrying these systems with you. I mean, some of the code I'm showing here is over 10 years old, which in terms of code is quite old. Now, of course, if I can slice in 2D, I can extend these principles to 3D. That was one of my main interests years ago, and it was in subdivision and trying to have 2D concepts in 3D. So I spend a lot of time on getting the code running to do this, and then all these 2D concepts of defining grids could be extended. So you have these kind of volumes. Now the problem with volumes is, of course, that you display them on a 2D screen and you can't always see the interior. Or having these partial cut-throughs, giving these interesting structures which do not run entirely through. Again, an infinite amount of blocks of oatmeal in this case. The other thing that's nice is once, so we started from volumes and we had planes and slices modifying these. We can also reverse it and have why not define volumes by planes? Like I have here a collection of points and I'm taking a special interest in that center point. I'm collecting, whoops, wrong button. I'm collecting some planes around it defined by those points. And I can see that if you take those planes, they start to enclose space. And if you were to draw that space, you get this shape. Mathematically, this is the Voronoi cell of this point in that collection of points. And it allows us to do fun things like shatter a sphere, which normally runs a lot slower, but now goes very fast for some reason, so you hardly see it. Fortunately, I have other examples. And there is software on the market that does it for you. The nice thing about finding ways of doing it yourself and exploring it as a creative coding is that you might want to change things that the systems do not allow. You are not interested in physical properties necessarily. Sometimes you just want to have nice aesthetics. And for example, you want to change the way the planes cut. Sometimes you want them to throw a bit more away depending on how high you are, or rather how high the part is. It's not easy to do in computational geometry when high, so it's not advisable. Or you use it on a cube, or all kinds of variations. And I think my daughter still sleeps in a pyjama, which is actually an oversized t-shirt of mine, which has this drawing on it. And this one I always liked because it's a star, and if you have it a certain way you look at it, it's just a star which has been smashed a bit, but it's mostly intact. But if you rotate and you look at it another way, you get this kind of columns in it. So there's definitely structure in it. And if you find the exact right way, which I don't do, you see that it has been split in half. And the only thing that controls that is how the points were located that defined how it was smashed, which was accidental, but nice. Same thing with these more kind of spatial filling explorations, which have different behavior depending on where they are in space, more or less regular. I think I have two more of these. And I like how in these you have a general shape which is kind of preserved, but there's a kind of infinite variation which I did not impose, which I did not have to manually put into the system, but which emerged. And of course, if you break stuff, and you're a bit patient, the next step is gluing it all together again. And that's very typical of the iterative process that you would get when you start doing these kind of explorations with generative art of generative code. Yay, there you have it. Is that you don't start off from a certain goal, you start with a certain path and you just explore it and you go where it leads you. So back to our 100-veld, back to the 100-veld, where we have this 10 by 10. So maybe this Voronoi, maybe this local slicing thing would give us the control we want. And actually, turns out, not really. Turns out that 100 is too much. It's noisy. It's a pattern, but it's definitely balls of oatmeal. This one. But what if we just separated it? And this is where we ended up. We have our 10 by 10, and we do split it, but we split it in large parts, and we retain the local grid. And to make it a bit more interesting, we do something that is very simple for humans and which is very hard for computers. Namely, we take the pieces and we just reorder them. If we were to do it manually, we just do it and our brain processes it and it will make a kind of shape. And if we would say to our mind, we want to make it as compact as possible, we will do it. But once we try to have our computer do it, it becomes hard because we have no way how do we tell the computer to do what I just did, because I actually don't know myself what rules I followed when I put down this piece. So this was an interesting challenge. But it kind of worked out. And there we have it. There we have the foundation of the visual design of the order of operation, flyers and posters. It's quite fun to make it, actually. Superimposed on that, we have our grid, and we can use, so we want to have the association with the number 0, actually 1 to 100, and we did that by coloring the 100 squares according to the number they represent. And that, since the grid is preserved, that goes all over the place, and that's how we get these kind of things going from 0 to 25 to 51 to 100. That was also a nice challenge, because from 0 to 100 are 101 numbers. But a grid of 10 by 10 is 100, so it was, but we found a nice compromise. Okay, so that's it for the 2D 100-veld. Then there was actually the question, can we use some animations for the website, for promos, to have it on the screens? And the only animation I had of these is this, and to be honest, I couldn't figure out how to make these more interesting. You have pieces sliding through each other, which I don't like. It goes all over the screen, so suddenly everything is outside the area you want to look at, so it was very hard to control. So I went back to something I was more familiar with, that I played around in the past, and that's, instead of having this, we have this. We have the no longer a 100 field, but still it has the same visual style. And remember that we know how to slice, so we can slice this thing. And one of the explorations I'm fond of is, if you slice something and you take one part and you slide it along, it's still one thing, and it still has the same volume, it's still one unit. If you slice it again and you rotate, it still remains one thing. The volume is the same, it's one unit. And somewhere in there, that cube we started from is still perfectly preserved. We can take these parts and we can put the cube together again. And we can repeat that as many times as we want. And I like these kind of feature preserving, volume preserving manipulations that can be reversed, undone, which kind of hide what is happening. If you would not put this cube back together again, you would have all these pieces without a clear history of why these pieces are that way. And that finally become the piece. Now, for this presentation, I gave it some colors. It doesn't have to be monochrome, and it doesn't have to fit the team entirely. And behind the screens, of course, this is all math which is running. The points, which are vectors, all the manipulations, the rotations, the shifts, all these are matrices. And it's a very nice thing, but it would take us too far to see how the properties we expect from real life, like if I have a piece and I rotate it and then I shift it, or first I shift it and then I rotate it, that the end results are different. That's something we know in our mind. If we multiply matrices, we have the same properties. That is very abstract for us. But those two things link completely. And it's very nice to see how our mathematical representation actually leads to the same conclusions as our real life experience. I think it sounds a bit trivial, but I think that's quite an extraordinary thing, that we have this kind of language, we have these kinds of objects, you can study them by themselves, and the properties that you learn from them, the things that you can prove with them, have real life repercussions. Now, it's a generative system, which means that I can adjust the rules, so use only translation, use only rotation. So these were some of these experiments. Or we can just use different kind of operations which preserve volume, like squashing and stretching, like skewing. These tend to break up the volume less, but they are less controllable in how it appears on the screen. Or we can just change the base shape, which will very strongly change the appearance of the kind of images. Now, one disadvantage of this kind of work is if you show pieces like this, you get questions like, oh, we are very much interested in this. Can you make a system where it changes into the letter B and then back? And that's no, I have no idea how I would do that. Because the end result, this very nice multi-scale shape, is not something I have direct control over. It's a result of the rules. And there is no rule set that gives me a letter B. So often then you can find some compromise and you have to manipulate the system a bit, which is not very pure, but still, it's what you can do. And then we come to the system called add nothing, subtract nothing, which has been derived from this. Actually, this was the precursor of what I showed. The order is not, it's nice for the narrative, but the real order is reversed. And the name add nothing, subtract nothing just comes from the reason I told that these operations, these rotations, these translations, they do not change the volume. They keep the shape. And when you restrict, go back, when you restrict the system to shifts and 90-degree angles, you get, now I'm doing one operation per mouse click, and these are actually the things which has been plotted for the exhibition. And the beginning shape will determine how these intermediate shapes look like. But the other things that control it is where do you define your random planes and things like that. So these are quite central here, so that preserves some of the unity. And you can go on. The small animations that were used of the rotating cubes, they used about 8 operations. For the plots, we go up to 150, and then you get very, very spiky stuff. The system has actually been written from start to be able to be plotted, because it's not that easy to have 3D objects and plot them. And so if you have the opportunity to still visit the exhibition, there's a series of 24 plots of these kind of systems. If you have already seen it, thank you very much for that. And now I actually end up at a place that I have a mad story to tell, but I don't know how much time is left. Let's make a brief math. I think in 10-15 minutes I can do it. And if people want to leave, please leave. I mean, I can't leave, I'm here. And it's actually a story about this. It's a story about a pendulum. Because let's see, do we still have sound? Yes. I started off with saying that generative art is not a medium. And I've been demonstrating that generative art is a technique. But is it more than that? Is it also a philosophy? And I think it is. It's not all generative art has this philosophy, just like not all cubist art has the same philosophy as the people where it originated from. It's inevitable that certain time aesthetics get, how do we say, that aesthetics become a goal on itself, and so you have impressionist art from people who are not impressionists, you have cubist art from people who are not cubist. The same with generative art, but I think there is definitely a philosophy. And this simple thing, I hope, will help to demonstrate it. And how we see this kind of depends on how our background. If we are physicists or engineers, we will see this as an approximation of a pendulum. Brecht, I stole your necklace. Is this visible in the light? I tried to find a shiny thing, this pendulum thing. I hope you can see it, otherwise this is very silly, the way I'm standing here. Nice thing about a pendulum is 1, 2, 3, 4, 1, 2, 3, 4. And now I take a small angle. It's 1, 2, 3, 4, 1, 2, 3, 4. It's the same rhythm. Large angle, 1, 2, 3, 4, 1, 2, 3, 4. Same rhythm. Change the length. 1, 2, 3, 4. It goes a lot faster. But this pendulum doesn't seem to care with how much force I pull it, how far I pull it. It only cares about the length, which is a physics thing. I don't know if many of you have seen this thing in physics in secondary school. Not thing is, as an engineer or as a physicist, we see this as an approximation of a real pendulum. But maybe in mathematics, we see this pendulum, this real thing, as an approximation of this mathematical thing. This is a mathematical object, a construct. It's some kind of thing, theta, which changes in time, or just as a function. And my background is physics, so for me that's a representation of something changing in time, but you can see it as a purely mathematical concept. You don't need to tie with a real life thing, so it's something changes equals something else. And you can explore that mathematical object without a connection to what is going on with the pendulum, but we're not going to do that. But it is important to realize that every conclusion, everything we see, everything we come to, is already captured in this abstract mathematical construct. It's in there. It's not something that we have added by drawing it, by interpreting it as a pendulum. It is in there. And the straightforward way is, of course, our pendulum goes back and forth, and it creates this kind of curve. And I call that X, and I call this Y. That's a way of graphing it. Now, this way of graphing doesn't really make sense. It doesn't add any information for me as a physicist, for an engineer, or for someone seeing this as an animation of motion graphics of a pendulum. It doesn't add anything. What we can do is look at some other things. We can look at how this left-right changes with time. We can check how the up-down changes with time. Or maybe we can look at the angle, this thing that was in the equations, with time. Or how fast it goes with time, or how fast it goes with angle. Suddenly we have all these possibilities to look at it. How fast it goes with angle is an interesting one because time has disappeared. Suddenly we are looking at this object and we have removed time. So this circle it describes tells you something very fundamental about this object, but not in the human perception of this thing swinging back and forth. What we also can do is time how long it takes to change direction, called the period. It's very boring, it's only 1 point. There's one pendulum, it's 1 period. But what I like as a physicist is how this system represents energy moving between 2 reservoirs, 2 containers. And 1 container is height. I'm moving this thing against gravity, and that takes force, and as energy goes somewhere. The moment I release it, that energy is free to be converted into colliding with my hand. If this pendulum is at its lowest point, it's moving the fastest. So at that point, all the energy it had from lifting it against gravity has been changed into energy associated with movement, kinetic energy. So forget all that. The yellow and the purple are 2 reservoirs of energy, and this pendulum is just switching energy back and forth. And if we have many, many, many pendulums, we can just run them. Now this is chaos. I mean, there is no order or anything in it. We just took a bunch of them, changed them. And there is something nice about it. I like this, otherwise I wouldn't show it. But maybe it pays off to be a bit more systematic, like let's keep the length the same and change the angle and just release them. And what we see here is what we have been taught in physics, or maybe you know, or I just told you, that they swing in the same time. So all these periods are the same, and they kind of are synchronized. Not completely, there is something fishy going on. They are not completely synchronized, but they are pretty much synchronized. It doesn't really matter. And this is what you will see if you are at the children's playground and you're at a swing. If you're not the show-off that goes all the way up and all the way down, you will swing. Whatever you do, you will always be in sync with the ones next to you. If they go up, you go down, vice versa, or you are in sync. And it doesn't matter if this person is 20 kilograms or 80 kilograms or 160 kilograms. Two swings next to each other. You normally swing, you are always in sync. And the rhythm you have to push is always the same. What happens if we change the length? Now, we know that should change something. And indeed, it's just a fun motion to see happening and to see the waves rolling through these schematics, which suddenly become, instead of representations of information, becomes very nice things to look at all by themselves. For example, the way that these graphs, if you just put them on next to each other, it's quite relaxing to see this rolling, waving surface. It changes a bit when we exaggerate. Then it's no longer this very simple story that we have been told, the story of the pendulum, that its period is independent of how high you do. It's actually not true. It's only true for a certain range of angles. It's so-called the small angle approximation. If you go all the way up, you still get nice patterns, but the movement is far more complex. It's no longer going like a rhythm, like a sine wave. There are humps and little deviations in there. And the story that we have been told that these pendulums don't care about their length. If you look at the period for the larger angles, it's no longer true. We don't no longer have the nice flat line, it goes up. And in theory, if you would be able to put the pendulum all the way to the top, it wouldn't fall down, and you would get an infinite period. But exploring these, you get the opportunity to have these kind of curves, which represent this mathematical object or this physical toy model, which you can pretty much invent by yourself, but it's nice to see them appear. They, in my experience, they always have subtleties underneath which you don't have when you just invent something firsthand. Or this kind of motion pattern which gives you the angle versus the speed, where every arc is one pendulum. And you see how they slowly start to diverge from each other, and they create this kind of shape, which is not round, not perfectly round, but it's just still rotating. And it's a very hard shape to make otherwise. Now, what is the story about this? Why am I showing this? Well, it has to do with how we view the world. This pendulum is what we call a simple system. If we start a bunch of pendulums close to each other, or farther, or even further away, okay, if we wait long enough, they just go all over the place. There is no connection with them anymore. At least when you look at space and time like we usually look at it. If you look at them as mathematical objects, where this time has been removed, you see that they stay pretty much bunched together. This is a system that tells you if you are reasonably accurate in the beginning, you will remain reasonably accurate. The system doesn't explode. And systems like that have a very interesting property. They are predictable, and they are controllable. So here we have again our full range of pendulums, but now we have built a central bank of pendulums in the system that is monitoring this and saying, this pendulum is going too slow, I'm going to shorten it. This pendulum is going too fast, I'm going to make it longer. And it's going to continuously monitor what's going on and change the pendulums until, in the end, we get this. We have found a way of have a completely harmonious system, which in theory is buildable. So if there's an order of operations 2 and you're looking for an installation to build, this one would be a fun one. So, and that kind of systems give us hope, because that kind of systems is what we as humans want. And we want our economy to be like this, and we want our democracy to be like this, and we want everything we set in place to be like that. If we are more or less accurate, if we are more or less right, then maybe everything will be fine. Unfortunately, mathematics has a say about this. Because let's go, for the last few minutes of this talk, let's go to its slightly more complex brother, the double pendulum, which is a pendulum which you attach to a pendulum. And it's, yeah, you see, this one is quite well behaved. This one is also quite well behaved. Swinging back and forth, bit of a, yeah. And then it starts messing up, or start messing with us. Because then you suddenly start asking, what are you doing? This is a notoriously difficult system to simulate, by the way, so, but I promise you this is a physical, accurate simulation of a simplified double pendulum. It is really behaving like that. Okay, but that's just complexity. Maybe we can handle additional complexity. The curves are no longer circles and simple waves. They go a bit all over the place. I actually quite like how these curves wander off, because they have this nice correlation between speed changes and angles. So they feel very organic, even without knowing what is behind it. If you would see a curve like that, you would suspect that there is some real system behind it. It's very hard. Now, part of the clue is we don't have 2 energy reservoirs, we have 4. Each of the pendulums have their own 2 reservoirs, and these are linked in all kinds of ways. So there is no simple way anymore of energy of going back and forth. Energy can be split all over the place. So that's kind of a clue what is going on, why this double pendulum is certainly not just the simple pendulum's more complex brother. So I'll just skip this one. So you can imagine if you have a bunch of, then, okay, yeah. No chance of making any meaningful conclusion. And what you always will see is that if you would look at the period, how much time it takes to go back and forth, that is no longer a simple number. It changes all the time. So it's no longer a simple dot. And that is because those 2 pendulums are pulling and pushing each other and changing their periods. But still, we can try. What if we know something about the system? We still have a chance of controlling it, of predicting it. So we just change this little angle. And yeah, this is still reasonable. I mean, it's not going to be that accurate as a simple pendulum, but at least all these graphs give shapes that we can describe, and we can at least say something about it. How about this one? This is the one that we could control in the case of a single pendulum. So I'm running this one a bit slower because it's very, very sensitive to errors. And basically, there's no chance to find any kind of uniting. It really, this one explodes all over the place. Especially if you would look at the speed of one compared to the speed of the other. You get this very intricate curve going. which you could trace purely for aesthetic reasons. I'm not that good at making like rolling waves or nicely evolving surfaces. I need to simulate double pendulum behind the screens and then plot angular velocity versus angular velocity. So that would be my approach for this system. Why this double pendulum system? Because here we now have a system which has a very, very tiny inaccuracy. Something where with a simple pendulum, we don't really mind because we know that everything sticks together. And here this looks, so my economic prediction works, everything is nicely together. So I can make a new rule and I can decide on some things, and then the weekend passes and it's all over the place. And suddenly I need a central bank to grab everything and restart everything. Or suddenly we seem to have elected Donald Trump. So something on those systems is quite difficult to control. And that is for me something philosophically, something fundamental about generative art. Generative art is the art that explores processes, what happens with simple rules. Because we have been preconditioned in the way that we have been taught, in the way that our cultural history is preserved, that simple things and simple rules lead to simple systems that we can control. And we are running into problems because that is no longer true. And one of the factors that contribute is the fact that we are closing feedback loops all over the place. And closing feedback loops, that is moving energy from one system to another. And it's a prime condition you need to have what is in mathematics called nonlinear behavior. And it's what we are being confronted with. And for the moment, we have this huge divide in our mindset. That on one hand, we have these simple systems we think we can control. And on the other hand, we are running behind them, trying to correct all the time. So that was the mathematical allegory I wanted to tell. Thank you very much for the extended time.